Hi everybody, welcome back. So having my morning coffee here, and before I get this Kenwood off the bench, I thought I would answer a burning question that keeps coming up on the channel. And that is, a lot of times I have people say, why do you upgrade the capacitors in the power supply of an amplifier, and how much, when should you do it? Is that right? Isn't it designed correctly in the first place, and so forth? And the first thing I want to answer is that I did do a video on linear power supplies, and we went through the math, and then we actually set it up on the bench and did an experiment where I showed that it's actually diminishing returns as you add capacitance to your main power supply in your amplifier. A big increase in capacitance gives you a small decrease in ripple. But there were some caveats when it comes to dynamic power and things like that. So what I thought I'd do is a very non-scientific test. We're going to do two tests. Test number one, we're going to look at just a low frequency sine wave, like 30 hertz. And we're going to turn it all the way up until you start to see some distortion on the scope. And then we're going to do a dynamic test where I have my signal generator set to put out just a single big pulse of a low frequency sine wave. So it's not a continuous, so it's just going to drain the capacitor very quickly and then stop, and then the cap will be able to recover. So we're going to do those two tests, and we're going to do those two tests with the original power supply that's in here. And if you remember, it only had 1,000 microfarad capacitor for the main feed for the whole amplifier, and I doubled that to 2,000 microfarads. But that's still pretty small when you compare it to some other amplifier designs that are out there. And we're going to compare, then we're going to just tack on randomly a large capacitor. I'll take like a 4,700 microfarad cap, tack it into there, and we're going to see if it makes any difference whatsoever. And we're just going to look at it. We'll do the same two tests with our scope and see what kind of difference it makes. What I'm going to show you is that you can sometimes get a little bit of a difference, but really there's more limiting factors than just the capacitor. You have to have a transformer, and the rectifiers, everything has to be able to handle that kind of surge current in the first place, or the capacitors will not be able to do their job. That being said, there is a difference between continuous power and dynamic power. Hopefully we'll see a little bit of that when we do this. So if that sounds interesting to you, stick around. We're going to do that, and who knows what results we're going to get. We'll find out. At the end of the video also, I will address some really good questions I had on the final video of this Kenwood TK80U, and that was, there was a clip missing when I edited the video. And what I found out is that the main part where I discussed what I did to actually make the multiplex section work properly, the majority of that got cut out. So I'll do a little, if you're not interested in that, that's fine. I'm going to tack it on to the end of this video. But you can actually, if you want to watch, I'll talk about it a little bit so that you can at least see what I found to repair it. So let's get to testing. So let's set the scenario. First thing we want to do is kind of get a baseline. Let's see where this amplifier distorts at 1 kilohertz. You know, that seems to be a pretty standard frequency that people will test things at, is 1 kilohertz. Having a drink of coffee here. Let's turn it on. And you can see right there, I'm on the one channel, I'm getting a little bit of oscillation. And part of this is because the newer transistors that we used have a much higher transition frequency than the older ones. And so they have a little tendency to oscillate a little bit at maximum power. But you can see this thing's putting out about 30.9 watts or about 31 watts. And actually this channel probably could go a wee little bit higher before it'll start doing the same thing. See it right there? Now they're both doing it. This guy's clipping a little bit harder than this guy, but they're very, very close. And probably I could turn the balance control and, you know, get it really even. There you go. So you can see 33 watts, 35 watts right there. So long story short, we're getting about it's making its rated power. This is rated at 32 watts per channel into 8 ohms. And you can see we're very easily getting that. Now let's go down to 30 hertz and see what it looks like. I'm now down to 30 hertz, and let's take this up until it distorts and see what kind of power we're getting. And right there you can see it's distorting. You're not oscillating anymore, but you are getting distortion. So let's back it down just to that point. All right, that's about it right there. And you can see we're only at about 27 watts. So we do have decreased power. And you can see as we let it go more and more and more, it starts to creep in. And notice how it's starting to distort a little bit, and then you can see it creeps back out. Did you see that? That's the actual thermal tracking circuit working in the amplifier. In other words, the transistors are heating up right now because they're running full bore. And what happens is those transistors will drift off of bias, and then that bias circuit heats back up and it kind of tracks with it. You see that? So bottom line is we do have, it's not clipping properly. In other words, we really wanted to see the top and bottom clipping, but we're not getting that. See what it does? So keep that in mind. That's our first test. The next thing we're going to do is called a dynamic test. Let me get set up for that because it takes a minute to set it up. Our next test is called the dynamic test, is what I'm going to call it. And what we're going to do is we're just going to put a quick burst of 30 hertz. And it's actually only going to be 5 cycles of 30 hertz. So you'll only see 5 cycles there. And that's it. And why are we doing that? Well, that quick burst of power represents like a heavy bass passage in when you're listening to music or something. So what that means is that normally when you're listening to something, the amount of power that you're listening to is not that much. Your ears can actually pick up the mid-range at a much lower power level. However, when a large bass note comes in, it quite often will spike the power way up. And so those are those are only instantaneous. It's there for a second and then it's gone. And that's really where your capacitor bank will come in. If it's an inadequate capacitor bank for the power for the amplifier, what'll happen is you'll see the first cycle will look very clean. The second cycle will either reduce a little bit in amplitude or start getting a little bit distorted looking, and each one will get progressively worse. If you see that, that's a telltale sign that you don't have enough capacitance in your amplifier. If it looks clean all the way across, then your capacitor bank is adequate. So let's do that right now. And there you go. So what you're seeing is we're going from no signal right here to a 30 hertz signal. And you can see I have it set so that it's just barely distorting. And you can see as this thing goes across here, it's staying very stable. In other words, this distortion is because I'm overdriving the input of the amp a little bit. I'm driving it into clipping. But what you can see is that it doesn't change. In other words, if this was real high amplitude and then this one was smaller and more distorted, that would tell me that the capacitor bank is not keeping up with the amplifier. But as you notice, it's staying pretty consistent there through that 5 cycles. And if you look at the power, we're still only getting about 20 watts per channel. So now let's add a 4700 microfarad capacitor to the power supply and see if anything changes. How's that for a bodge job? So these 2 blue capacitors down here are the main filter capacitor for the amplifier. It was originally a 1000 microfarad capacitor in there, I believe is what it was. And I put these 2 1000s in parallel. So actually there's 2000 microfarads. Now why did I do that? After I went through all of telling you that it really doesn't make a difference. Well, I did it for a couple of reasons. Number one, when this amplifier was built, capacitors were very expensive. And one way they could save money was by putting the absolute bare minimum required to meet the specifications of the circuit. We have the advantage today of inexpensive components, so we were able to do this. So number one, we're going to exceed the rating a little bit. Remember, it's diminishing returns. Number two, by putting 2 capacitors in parallel like this, we're effectively reducing the ESR. So having a low ESR in the capacitor is good because, again, that's going to help with our dynamic range. Number two, that's also going to help with high frequency response of the amplifier. Number three, as this thing ages, if that capacitor starts to drop a little bit, we still have enough headroom that you'll still have plenty of capacitance for the amplifier to stay in spec. Now, why would you not want to do this unless you know what you're doing? Well, whenever a capacitor is discharged and you turn the power onto the amplifier, these capacitors almost act like a short circuit for a split second. And because of that, this transformer is going to have to deliver extremely high current, as will the rectifier diodes. If you put too big of a capacitor on this transformer, you could damage the transformer, or more likely damage the rectifier diodes because of the surge current when you're first charging them up, unless you have a soft start circuit. And I explained soft start circuits quite a few times in some of my other videos, especially on the Pioneer SX, the 1050, when I did 2 different series on those, and in both of those I explained what a soft start circuit is. Without that, this transformer is going to be subject to very high surge current. Now with a 2000 microfarad capacitor, that's relatively low, and I happen to know that it will not hurt this transformer. It's more than big enough to handle that. Now, going to this size, it's not something I would recommend leaving in here permanently without modifying some things in the circuit, like putting in a soft start circuit. But for just this one time, it's not going to hurt anything. This transformer will be fine, and these are way oversized diodes I put in here that can more than adequately handle the surge current of this. So what we have is, this is a 4700 microfarad capacitor, and along with the 2000s, and they're all in parallel, so they add. So what we have is 6700 microfarads. So we've really increased the capacitance of this output. So if changing the capacitors makes a difference in how the amp performs, this certainly is an overkill situation, and we should certainly see the improvement. So let's go back and do our original tests again with this big capacitor in here and see if it makes any difference. So once again, let's do our baseline. We're going to do 1 kilohertz, and we're going to drive it into clipping, and let's see what happens. and there's clipping. And notice there is no oscillation. The oscillation's gone, and we are now at 33.1 watts per channel. So the power hasn't gone up a whole lot, just a tiny little bit. Let me take it down out of clipping again. And it's right around that 32 watts. So the overall maximum power, if you notice, hasn't changed. But it definitely cleaned up the waveform, and we are definitely not getting that oscillation anymore. You see, it clips very cleanly now. So that's a surprise. I didn't expect that. Let's go to our 30 hertz. Okay, we are now at 30 hertz. Let's turn this up and do our same test. And we'll bring it right up to clipping. And you can see it doesn't notch nearly as bad anymore now. That's a lot better looking clipping. And look, I'm at 33 watts per channel right now. If I go down just a slight bit, that cleans up pretty good. And I'm at 31.75 watts per channel. So at 30 hertz, it improved the performance of the amplifier as well. I guess I'm going to eat my words on this one. When I started this test, I did not believe that this was going to make any difference whatsoever. So why did I not believe it was going to make any difference? Well, because I didn't think that the transformer in here was capable of delivering that type of current. I thought it was the limiting factor. But it's looking like the capacitor was a limiting factor. Now, we need to do the dynamic test, and that'll be the final determining factor. But if you remember, the dynamic test showed that there really wasn't a problem with surge current, but you still were getting the distortion at a lower amplitude. So let's see if it cleans that up as well. So let's do our dynamic test now with the added capacitor and see if it makes any difference. Remember from the last time we did the dynamic test, we got about 20 watts and we were getting some distortion of the signal. So let's see what we get now. And the first thing I notice is that the distortion is gone, and I've left everything the same. And second of all, what we notice, take a look. We're now up to 21.4 watts. So the dynamic power performance of this has gotten a little bit better. You can see we have a wee little bit of distortion here and a wee little bit of distortion here and here, but the rest of it is a pretty clean looking sine wave. Now, this floating around here has something to do with the output decoupling capacitor of the amplifier and the oscilloscope triggering and some things like that. But what we're seeing is there was a slight improvement by putting a larger capacitor in there. Well, I don't know about you all, but I was a little bit surprised by this. I did not think it would make much difference, if any difference at all. Because usually when these amplifiers are designed, they're designed to work properly across their entire power band. And this proves that Kenwood probably cut some corners on the capacitors because of how expensive they were. Back then, that was one of the more expensive components in a receiver at the time. So adding that extra capacitor made a big difference, and it made this amplifier a lot better performer. Not only did it allow the low frequency response to match the higher frequency response, it eliminated that little bit of oscillation we were getting in the output section. It improved our dynamic power a little bit. It overall improved the performance of the amplifier. So I guess in this case, this amplifier could use, could be improved by increasing the output capacitor. So maybe, just maybe, I'll leave this in there. I don't know. Or I'll redo it to make it, to make it a little bit neater. But regardless, I would say we made a big improvement on the performance of the amplifier. So there you have it. Again, I'm a little bit surprised, but there it is. Now, that being said, I don't want you guys to go out there and start hogging in great big capacitors in every amplifier. This is a exception more than a rule, especially when you get into the receivers of the 1970s and so forth. They were starting to get that down to a science, and what was in there was what belonged in there, and changing anything there really will either do nothing at best case, and at worst case scenario will make things worse. But in some of these older receivers that have undersized components like that, you can see that, I guess, there are ones out there, this being one of them, that can be improved by it. Understand that you have to know what you're doing. If you put a capacitor that is too big for the transformer or the diodes to handle, you can damage something, and that will cause a lot of problems. Especially if you short a diode out and now you're leaking AC, you'll damage the capacitors, and you possibly will blow transistors off on your amplifier section. You can cause a lot of damage. Don't do this unless you really understand it. If you want to know more about this, check out my video on linear power supplies, and I really need to maybe kind of categorize some of my videos and organize them a little better, but yeah, that'll be on the list. Anyway, there you have it, and you can kind of, let's discuss it down in the comments section. Tell me your thoughts. I'm a little bit surprised by it. So as I promised at the beginning of this video, I'll just give you a quick explanation of what I did to repair that tuner problem. Let me show you a schematic. So some point from where we ended off with the original schematic that was wrong, and then we came up with this redrawn one that I did that is correct, I missed some video footage that really would have helped some of you understand what we did. First of all, this is the reverse engineering of the board. All I did was I went through every component. I went through the traces on the board. I took my ohm meter and I just rang out the continuity and the resistance between all the points and compared them to the original schematic, and then wherever there was a difference, I just printed this out, this blown up section of the schematic, printed it out like this, and then I just took white out and I whited out whatever section was wrong. Then I copied it and I took that photocopy and I drew in the components as they should be. So these used to be, in the original schematic, they were PNP germanium transistors, and our amplifier had NPN silicon transistors. The amp was capacitive coupled in the original one, and in this one it turns out this was a direct coupled circuit. So we eliminated that capacitor altogether. It was just direct coupled. The values of these resistors were different. Obviously in this section they have to be different because it's, instead of biasing a germanium transistor, we're biasing a silicon transistor. So that of course changes all the values of these resistors. This voltage divider right here was different because you had two separate voltage dividers before. There was actually a resistor going from here to here, setting up the voltage divider to bias the base of this transistor, and then there was a capacitor that was decoupling these two circuits. So with that being eliminated, this was eliminated when you went to the direct coupling. Anyway, what fixed this thing? Well, there were two main things that fixed it. First thing was After seeing what these values were in here, I measured these actual resistors and compared them to what the little color band said on the resistor, and they were grossly out of tolerance. I don't know if this amplifier was in a damp environment. I would think that if it was, this metal chassis would have a lot of corrosion on it. There was no corrosion on this thing, very little. So I can't really, other than the resistors just drifted in time, over time, I can't explain why there were so many components that were out of tolerance. The other thing is, a lot of these transistors that have these little metal cases, some of them will develop what's called tin whiskers. And what it is that the plating that they coat these metal cans with, inside and out, will actually corrode, and you'll start to get these little metal, they look like whiskers. And they'll get in there and they'll short out the elements of the transistor and cause noise and cause shorts and all kinds of strange things. So there was one or two transistors that were noisy. I don't think they caused the main problem, but they certainly would have added to the noise factor. So I replaced those. But that really wasn't the big problem. The drifted resistors was one. I'll show you the other. Going back to the main schematic, if you look at this, the demodulating section here, where you come out of the transformer and you have your multiplex mixed with your 38 kilohertz, and then we demodulate it through here, we have these two little balancing pots, and they're supposed to be 50K. One of them was 76K, the other one was 90 some K, almost 100K. They were extremely out of tolerance, and this wreaked havoc on this circuit, and this is why we weren't getting separation. Now, that's not why we were not getting the same amplitude on here. That was the drifted resistors that caused that mainly. But this definitely was causing, we weren't getting proper mixing of the signal, and we were not getting that. Because of that, we couldn't get separation. As soon as I replaced those, everything kind of fell into place. This was a lot easier, to adjust, I should say. The other thing, and I think it did make it into the video, but I'll repeat it just in case it wasn't, because I didn't go back and check it. This coil here had a double peak. The first peak that I originally had it on 2 videos ago was the wrong one, and it had that terrible notch in it. I was getting the 38 kilohertz, but it had that horrible notch. When I drove that coil all the way through the center and out the other direction, I picked up a second peak, and that second peak was a much cleaner looking sine wave, and that's the one that you saw on that last video. So properly tuning this, replacing these 2 pots, and replacing all the bad resistors in here fixed the problem. But that's it. Getting an understanding of it helped me to understand how these bad resistors would cause the problem. So, bad resistors, 2 bad pots, Tony tweaked this wrong. Those 3 things fix the problem. I hope that clears it up. I'm going to keep my day job because I don't think it would work out so well, my being a video production person. So anyway, all kidding aside, that's it. Again, I wish you all peace, joy, happiness, and good health in your lives. I hope this video was entertaining, and we'll see you next time. Take care. Bye-bye.